This conference will now be recorded.
So, good afternoon, Padmini, and welcome back to a fresh new session on time series modeling for the market sessions. And we were talking about the ER processes. So, we were talking about the auto regressive processes, and we are trying to understand that how is it that this autoregressive, what exactly are the autoregressive processes, what are their key features, and how is it that we would define an AR1 process. And then we were talking about how exactly is it that this the data generating process for the AR1 time series models can be identified, right? The iterative process. And from there also we tried obtaining, we tried identifying how is it that the so how is it that uh, what should I say? So how is it that the uh, estimation? So how is it that the stationarity for these models are to be identified, right? Now, so how is what exactly is going to be the stationarity condition for the AR processes? Now, this is something that we had been looking into. Now, while we were talking about these methods, right? So in the last session, we had stopped at a point where we looked into the key moments for the AR1 processes, right? So before we start off, let's very quickly summarize those findings, and from there, we'll take the discussion. So for the AR1 process, so for the AR1 process, uh, what so we need to so we'll just very quickly look into what the key moments were. So first of all, the mean of the time series model. The mean of the time series model. So what is this mean of this time series model? The mean of the time series model is rho 0 by 1 minus rho 1. And this is a constant mean. So basically, if the time series is a if it's a stationary time series, stationary AR process, then this is what the mean of this series is going to be. Constant mean. Now the next is this is the constant variance. So one of the things we can see is that this time that the AR1 process, when stationary, has a constant mean, constant variance. Constant mean and constant variance. Now this is obviously one of the things, right? Now the next question that comes out over here is that if I have a constant mean and a constant variance, under what condition is this constant mean and constant variance obtained? So this is where this is where a constant mean and a constant variance is obtained. The third, so over here when we have this thing, so the question that comes out is under what condition? So the condition for stationarity for an AR1 process is that the rho 1 should be strictly less than 1. For greater than equals to 1, the time series becomes non-stationary. Right. So that's one of the important criteria that we have over here. So so the condition for stationarity over here is that rho 1 or the mod value of rho 1 should be less than 1. Okay. So this is mod rho 1 less than 1. So this is what the basic criteria is. Okay. Now the question that comes out over here is that so there are a few more questions which comes up. Number one is that what exactly is the covariance pattern or the autocorrelation pattern for an AR1 process? Now, if I have a mean constant process, if I have a variance constant process, then the covariance or the autocorrelation that we must have, so that autocorrelation then like my time series must also have constant of correlations, right? So the covariance between the two lags must be similar. So that is or they must be more or less constant again. So that is something that we would need to look in. And when I say constant means constant as in that the components composing them should be constant, but as the lags keep on increasing, the autocorrelation must kind of go down, right? So the autocorrelation must be a decreasing function of the lags. So this is something that we have with us over here. Okay, so let's have a quick look, or let's take a quick look into the autocorrelation patterns. So the covariance between two terms xt and xt plus k is so this gives us the covariance or the association between two lags xt and xt plus k, and divided by the variance will be your autocorrelation. So over here, let's look the autocorrelation to decrease across the lags, right? You should have uh, a covariance which decreases across the lags. So over here, I'm not going to talk about the, I'm not going to talk about the uh, derivation of this process. So I'll just write out the functional form and I'll explain why is this the most suitable covariant structure for the autoregressive process. Right? So over here, if you have a look into the covariance, it looks something like this: rho to the power of k sigma x squared. This is rho 1. This will be rho 1 to the power of k, rho I to the power of k. So sigma squared x. Okay. So now the question is that, so what exactly, or how do I interpret this? Now k is the lag. Now we have already seen that the mod rho 1 is less than equal to 1, or it's strictly less than 1. So if that is fractional in nature and as k tends to infinity, then the covariance should tend to 0 across the lags. So if mod rho is strictly less than 1 and k tends to infinity, then rho 1 to the power of k tends to 0 as the lags increase. So over a substantially long value of lag, the covariance declines, right? Now, if I compute the autocorrelation, so this is the property, right? So one of the things that you can see is that because it is a function of rho 1 to the power of k, therefore it is absolutely important that the conditions of stationarity on rho 1 is satisfied. So once you obtain the parameter estimates of rho 1, you should actually ensure that it is less than, significantly less than 1, because otherwise, if that is not the case, then your time series model is not a stationary model. Right, so all the characteristics of model stationarity, time series stationarity, will not be satisfied in this case. So let's move forward. Now the autocorrelation function therefore will be nothing but the covariance by the variance. So the autocorrelation between two lags, so the autocorrelation is nothing but it is the covariance variance of xt. So over here, the covariance xt plus k divided by the variance of xt. Right. So now if I look into this, you will see that the covariance which I declared or which we saw to be rho 1 to the power of k sigma x square divided by 1 minus rho 1 square. You have a sigma x square over here. So I'll cut this off, and what you will have here is okay. So rho 1 to the power of k divided by 1 minus this. Now, as k tends to infinity, as k tends to infinity, the autocorrelation function, right? So that tends to 0. So your autocorrelation coefficient between the two lags will tend to 0. Autocorrelation will tend to 0. Right. So what I have is rho 1 to the power of k divided by 1 minus rho 1 square. So as k tends to infinity, the autocorrelation tends to 0. So if the time series is stationary, you will see that the autocorrelation monotonically declines over a period of time. So if I just think about the absolute autocorrelations, so over here what I have is autocorrelation. I have autocorrelations, and over here what I have is lags, right? Okay. So basically, so how would the autocorrelations look like? So this will be the highest, then it should go down, it should go down. Right, so you see that this autocorrelation function gradually. Right, so the autocorrelation function should ideally decline. So given that the time series is stationary. So obviously there are a few important things. So the first and the most important thing is we need to identify that, or when we are, so this is the reason, why the stationarity must be there, because if the stationarity is not there, the autocorrelation functions will just explode and it will just keep on exploding over a period of time. So that is something that we need to take care of as well. Now, having done that, the next part is that we need to understand that how these uh, measures are done, right? So how is it that stationarity will be identified for a data set and so on? So how do I identify that a data set is for a given data set there is stationarity? How do I interpret the reports and so on? So that is the part that we'll talk about for. So that is the part where we need to see how it is developed in SAS. So for doing it in SAS, initially we'll take a data set and we'll put them in and we'll see, we'll try. So our objective first of all would be to interpret each of the results in SAS. That the result that the software is generating, we need to identify them and we need to just read through the results first. Once we have read through the results, right? So once we have identified, okay, this is what this report does, this is what this report does, and this is what this report does, then what we'll do is we'll feed it to a real data and we'll try uh, not only interpreting the problems, but we'll also try out solving the problems. So that's something that we need to look into. So let us start off with that. Okay. So just give me a couple of minutes time, Padmini, and just let me set up SAS and then we'll again start the discussion. Just give me a couple of minutes. I'm pausing the recording for some times and then we'll get started.
This conference will now be recorded.
So welcome back, Padmini, after the break. And to start off with SAS and rather with time series modeling in SAS, what we are going to do is we are going to look into, we are going to start off with a very basic data set that Box Jenkins had prepared, right? So the airlines data on which they had developed their ARIMA framework, we will be implementing the ARIMA framework on that. We'll be trying to understand the respective issues. We'll try to understand how this thing has been working on, and we'll try to understand how this uh, ARIMA models have been structured and how have they started coming up, right? And we'll try to interpret each and every tables which is generated in this ARIMA model, and from there we will start working, right? And once we have understood the generation of the results or the ARIMA results from top to bottom, then we'll go and start working on with it. So I have the okay. So let's get started with this. So let me first of all look into the the data on which we are going to build. So we will start off the basic representation of the identifying the basic contents of the data. Contents of the airlines data. That is the Box Jenkins. User proc content. So if we have a look into this, so this is the overall contents of the data. Now the name of the data set is the airlines data. The observation over here is, so there are 144 observations, right? And there are 5 variables which we generally we can use. So we'll see how this is structured and what are the variables that we have over here. We have date, we have month, we have passengers and quarters. So initially the date, the variable that we had over here was the date and the passengers. In the later stages, so in the next stage when we go in, we'll see that we would create some variables which would be these variable month, quarter and year over here. Right. So these are the very basic contents in this data set. So this data set has the total number of observations over here. Total number of observations in the Box Jenkins data is 144. The total number of variables in the data is so it's not calendar, it's time series here. So there will be 2 variables in this case. So there are two variables in this data, the date and the passengers. So there are two variables. Now one thing that we can do is we just print the first 5 records of this data set. Equal to 5. Just print the first 5 records of this data. We have the first 5 records over. So you can see that it is the month and the year given. So this is the date variable, and this is the number of passengers corresponding to each of the dates. Right. So this is where we are just printing the first 5 records, the first 5 sample records. Now from here, we will the next thing that we'll do is, because we need to look into trends and we need to look into the behavior of the variable, we need to look into the averages and all these things. So therefore, just having the date variable is not enough. Now, it is always suggested that you have the dates or the time variable aggregated at different levels. So let's say monthly level, yearly level, quarterly level, and so on. So we'll run this particular code. So over here, I'm using the month function to extract the month from the date variable. I'm extracting I'm using the year function to extract the year from the date and the quarter from the date, right? So what I have over here is the date function. So month, this is the function used to extract the month function, the month from the date variable. From the date variable. The year, the function used to extract the year from the date variable. The quarter from the date variable. So we'll very quickly we have airlines data. First, let me put it over here. Yeah, so over here you can see that there are five numbers, so there are five variables. Now, with the proc content given normally, right? So if you just write the default proc content statement, right? The variables are listed in the alphabetical order. So variables are listed in the alphabetical order. In the alphabetical order under this. Under the basic statement. Basic statement. Using Varna will help us generate it in the variable list. In the creation of. So let me just use this option Varna. You have all the variables are listed over here in the creation order. Now over here, what we are doing is, let me run this 5. So one thing you can see over here, Padmini, is that you have the date, you have the passenger's name, you have the months, you have the years, and you have the respective quarters. Now, having done this, now what we are going to do is we'll start off with the ARIMA procedure. So, proc ARIMA or the ARIMA procedure is something which we would use to generate different results corresponding to this time series model or the corresponding to the time series data, right?
Tanmay, I have one question. So why is it that we are taking month, quarter, year,
Now, the reason we are
everything.
doing the month, quarter, and the month, year, and the quarter is because, when I am looking into, let's say I'm trying to access the trend, right? So if I can aggregate, or if I have aggregated time points, aggregated time information, I can look into the evolution of the variable at different levels. So I can look into the quarterly trend if I want. I can look into the monthly trend. I can look into the yearly trend. So that will help me in case, suppose I see some issues of non-stationarity. So if I have my data created such that it is aggregated at different time points, then I will always be able to, go ahead and create this or go ahead and investigate them at a different time levels, right? So that is why the ARIMA, that is why this month, year, quarter, so this distinction is being done. So it will help me in deep diving. So otherwise it would not be very required. But you see that okay, there is a non-stationarity. You see there is a kind of a movement which is similar to a structural break. So what you can do is you can actually try deep diving into this and see, okay, why is it like this? How is it going on, and so on. So this would help us do that kind of an exercise. It's a deep diving exercise. So that is why the month, year, and the quarter is that is why we are creating these variables and keeping it handy for us. Right? Does that answer your question, Padmini?
Yeah. Thanks.
Okay. So now the ARIMA procedure, a proc ARIMA, is used to generate is used to look into the different time series result. Is used to assess different characteristics for the time series model. So I want to assess whether it's a stationary model. I want to assess whether I want to identify which is the most optimal model, and so on. So for that, what I'm trying to do is, although the procedure that we would use is the ARIMA procedure, right? Now, the ARIMA procedure uses, because it's a procedure step, we describe this data to the airline's data. Then what we have is we specify the variable for which we want to look into the behavior, and we specify and we want to assess the basic descriptive measures corresponding to the variable. So for that, for performing this basic function, right, identify statement. So before you start developing a time series model, even before assessing stationarity, the first and the most basic question that we need to address is what? The first and the most basic question that we need to address is that whether the model, in this model, I can use ARIMA. Whether can I develop this model using time series? So do I need a time series to develop this model? Can time series be used to develop this model? So these are the questions that we would first need to address. Now, when is it I will say that yes, I will need to develop, I can develop a time series model on this data? So for that, I need to look into the history, the correlation between the historical lags, right? And once I look into the historical lags, right? So once I look into the historical lags, and I see that okay, there is a significant extent of correlation which is going on, right? Then in such a case, I will say that yes, on this data, I can assess a time series. I can develop a time series model, because if that part is not doable, if you do not see that you have significant correlations across the historical lags, then that data cannot be used for a time series model, because that data will be a random data, right? So xt minus 1 is not explaining xt, xt minus 2 is not explaining xt minus 1. So if you have to develop the time series model, you need to ensure that the lags, the historical lags up to a certain lag is correlated. So there are significant extent of correlation across the lags. Right? So over here, let us first run this statement, run this code, and then I'll explain one by one what the thing is. Right. Okay. So over here, when we talk about proc ARIMA, or let me say ARIMA, this procedure is used to generate different measures to time series. Okay. A few important things. Uh, the output consists of several reports which capture stationarity and the model estimation results. Okay. Identify. So this statement is used to identify generate the descriptive measures for the time series model is variable. So the next part over here is your var. Var equals to option. So this is used to specify the variable, time series variable for which predictions are done. This is used to specify the time series variable for which the predictions are done. Right. Now, similarly, the in lags equal to option. Now, in lag, so this statement is used to specify the lags, the minimum number of lags, or the lags, specify the lags up to which the significance of correlations between the lags are to be estimated. Right. So over here, the first step that we are trying to assess is whether time series can at all be applied to the model. And this code has two main functions. The first is to describe the main descriptive statistics of this time series. So it clearly shows that the mean of the working series is 280. So basically on an average, there is 280 passengers. The standard deviation is 119. The number of observations is 114. So one of the things I can see is standard deviation is lower than the mean value. Now, this is an important relationship because in case your time series has a massive concentration towards 0, in that case your time series models will be, you cannot use your, so then there can be a concern and the standard deviation can be showing to be higher than the mean. Now that is something which is important. So okay, the identification of the variable. So over here, the first thing that we see is that the average variation is shown. So basically, I can say that okay, on an average, the number of passengers is 280, and then there is a plus minus interval, 109, a plus minus interval of 120. Right. Now this is something which is there. Now the next question which comes out over here is that there is a correlation, as I can see, and that this is kind of declining. So now I need to understand that whether the correlation, autocorrelation of the last 8 lags is statistically significant or not, right? So over here I have the correlation. Over here I have the covariance, right? And I have the standard error of each of these over here. One thing I can see is that at each lag, the standard error is also increasing, right? So now the question is that if these correlation coefficients are statistically significant, then I can say that yes, we will use time series models because within the last 8 lags, the autocorrelations are very statistically significant. Now to do this, I have the autocorrelation check for the white noise. The statistic is a chi-square statistic, obviously because this is a category of frequency type distribution, and the p-value is less than 0.0001. So the question that comes out over here is that what is it that the null hypothesis that we are testing? So the null hypothesis that we are testing over here is that the autocorrelation coefficients are white noise, so that these are not statistically significant and that they are identically independently distributed, versus the autocorrelation coefficients for the last 8 lags are not white noise, right? So from xt minus 1 to xt minus 8, so they are not white noise. The p-value over here is less than 0.0001. So the p-value, the probability of committing the type 1 error is actually very low over here. It's almost close to 0. So therefore, we can safely say that the alternate hypothesis is accepted. And given that the alternate hypothesis is accepted, we can say that yes, in this model, the autocorrelation check for the white noise. So we can say that yes, the p-value is close to 0, right? So it's very low, and hence what we will say over here is and hence what we would tell over here is that okay, fine. I have this autocorrelation over here, this p-value over here, it's absolutely low. Therefore, I'd accept the alternate hypothesis that these autocorrelations are statistically significant and there exists a significant autocorrelation across the lags. Therefore, each of the historical lags will be explaining the historical lags are in a position to explain the Th period. X in the Th period. Hence, the time series model can be applied to this data. So this is the first test that we are doing. Even before we are, entering to do a significance test, even before we are entering to do a stationarity test, the first test that we need to ensure is that whether we can apply time series to the data or not. After which we'll go ahead and we'll move into the next checks, right? Now the next part over here will be to break down the values into the different components. So I'll try to intuitively decompose it into seasonality, the trend, cyclicality, and then we'll see whether which of them turns out to be significant. If there's a trend, what type of a trend is it? Is it an additive trend? Is it a multiplicative trend? And so on. So for those things we have used these exercises, right? So we have broken them down into different time aggregation, and from there we'll try to. So once we have kind of distinguished, or we have divided them into quarterly trend, monthly trend, then we have looked into that and we have detrended them. We have removed seasonality and stuff from there. Then we'll go ahead with the estimation, right? So the next part that we'll talk about is to intuitive decomposition of the time series into trend, seasonality, and cyclicality components, right? So let's take a pause here for the day, right? And we'll start off with stationarity in SAS in tomorrow's discussion. Thank you.
Yeah, Tanmay, I have one question. See, if I were to do this in Excel, because I don't have one now. So if I have to do it in Excel,
Yeah,
so
I'll show it to you implementation in Excel as well. I'll show that. But
okay.
the reason I'm
Shall
using
I
SAS
just
to do this first part is so that you have an idea of the structure of the codes. So once you have, when you have it in your office systems or when you're deploying it in office, if you need it, you can use that. So then what I'll do is I'll show you the implementation in Excel as well.
In Excel, okay. I was just thinking maybe between today and tomorrow, what I can do is, see, I already have some deposit data with me. Okay. So I can take, say 1 lakh, 2 lakh, 3 lakh, like that. So do I work with raw data, or do I have to, convert it into some kind of percentage change or something like that?
No, that is a function of the requirement. So that's a part of the. So if you need to do that conversion. So there is no hard and fast rule. So that should be an iterative process. But to start off, you can start off with the raw data.
Raw data I will do. Is it okay? I will take that, and then I will just do a correl between the various
do a
columns.
correlation, do a basic regression, take one lag, right? Take a single lag, do a regression, a linear regression, take 2 lag, do a regression, and see which of them is giving a better output. Or very simply, what you can do is you can take YT and take YT minus 1, YT minus 2 like this, and find out the correlation matrix across all the lags. So you can do that as well. So that should also help.
Tell me the second one.
So basically, let's say you take YT to see a series, then you lag that series by 1, you lag that series by 2, you lag that series by 3 like this, up to 4 or 5 lags. Then find out, then create a correlation matrix with all these lags. So with YT, you look into the yt minus 1, t minus 2, t minus 3, t minus 4, t minus 5. Then across yt minus 1, you look into yt minus 1, yt minus 2, t minus 3, t minus 4, t minus 5. So it will be a cross tabulation. So that kind of a cross correlation matrix.
So everything, like where there is an intersection, it will be 1, 1. Otherwise, there will be some value.
Right, will be. So then you can see all type of correlation patterns which are involved in there.
Okay, fine.
And then you
can tomorrow.
Yeah, scatter plot, and then you can fit a trend line and see how the correlations are working.
Okay, done. Okay, thank you.
Thank you. Thanks a lot.